Okay, so welcome to everybody to this Graph Theory 2 course. We'll start with two lectures on algebraic aspects of graph theory. They're very, very rudimentary. There's no deep algebra coming at all. It's a bit more like it's borrowed from algebraic topology. So it's like one-dimensional simplicial algebraic topology, but it does have implications for graphs. Not all of those will be apparent in the first lecture, or even in the first two lectures. There's going to be two lectures on these algebraic aspects. And the first of them today is going to be really, really gentle and not difficult at all. Next time will be easy and not difficult at all. So we'll wind up a little as the course progresses. Right, so the basic concepts that I'll be introducing today are what is called the edge space of a graph. There's also a vertex space, which is defined analogously, which I'm not going to introduce here because it's not going to be needed. And there are two subspaces of this edge space, the cycle space and the cut space. And I'll tell you what these are today, and then we'll make a few observations about them. Right, so the edge space is the set of all maps from the set of edges of a given graph to F2. Every edge gets a 0 or a 1. And we can add these functions as you would by adding their images. So one function plus another function. What function is that? Well, you take an edge, look at the two images, and you add them. And of course, in F2, 1 plus 1 is 0. So the space of all these functions is going to be the edge space. So in topology, those would be one-dimensional cochains or one-dimensional chains because E, the set of edges, is finite. So it all comes to the same thing. Here, they're just functions from the set of edges to F2. And we can think of such a function as an indicator function, and then the elements that get a 1 are a subset of the edges, and we can think of that function as the subset. So if this is the set of edges of G, you might have one function, blue, that assigns a 1 to these edges. And you might have another function, yellow, that assigns a 1 to those edges. There are some edges left down here which get a 0 in both of these functions. So these get a 0 in both of them. And when you add them, these will still get a 1 because they get a 1 under the blue function and a 0 under the yellow function, and 1 plus 0 is 1. Likewise, these will get a 1, but those will also get a 0 because they get a 1 under both functions, and therefore 1 plus 1 is 0. They get a 0. So the edge set that corresponds to the sum of those two functions, viewed as an indicator function, is the symmetric difference between these two edge sets. Right? So addition of elements of the edge space viewed as functions from E to F2. When we reinterpret those as indicator functions, we get subsets of the edges, and then this addition is going to be symmetric difference. Right, the 0 in this vector space obviously is the function that sends everybody to 0. So that is the empty set of edges, viewed as a set of edges. And then there is a basis called the standard basis, which consists of the function sending one edge to 1 and everything else to 0. And that then as edge sets are the singleton sets consisting of one edge each. And that is obviously a basis, so you can tell from that that the dimension of this edge space is the number of edges, which we usually denote by n. Okay. Now, there's something like a dot product on these functions. When we have two of them, we'll just run through all the edges one by one, and then for every edge we take the image of one and we take the image of the other, and then we multiply those two. Okay, and so if you view this, if you take the standard basis and the coefficients, then that amounts to what you know as the dot product from linear algebra. But it works exactly the same here if you take as the set over which you sum the edges themselves, and then just take the two images, multiply them, take the edge, two images, multiply them, do that for every edge, and then you sum them all up. Right? So that's the dot product of two elements of the edge space. Just a word of caution, right? So you can have elements of the edge sets, of the edge space, or subsets of the edges, which dot themselves give you 0, even though these themselves are not 0. Can you think of when this will happen? Yeah. That's right. So take any element of the edge space that makes an even number of edges, assigns a 1 to an even number of edges, or equally a subset of the edges that is even, has even cardinality, then that times itself gives an even number of 1s, and when you sum them all up, then you get 0, precisely. Okay, so that's the dot product. And now there's also something like an orthogonal space for every subspace. So consider an arbitrary subspace, curly F, of the edge space, curly E. Then the space orthogonal to that consists of all the, whoops, wrong button, consists of all the elements of the edge space that are orthogonal to every element of this given subspace, right? As you know it, the set of all vectors that give dot product 0 with every element of the subspace. And the thing to observe here is that this orthogonal space can intersect the original space to which it is orthogonal non-trivially, right? That's because, well, same idea as what we just saw a moment ago. Okay, so that's the definition of the orthogonal space. And we have a dimension formula that is exactly what you know from linear algebra, even though you know it over R or C, complex numbers. The dimension of a subspace plus the dimension of the orthogonal space is the whole dimension n. right? And so that is the case even though these two can intersect non-trivially. So you might think that this shouldn't be true. How can the dimensions add up and they have a common intersection all the same? But it is true, and here's a little proof. So write down, take a matrix, and for every edge, we take a column. No, I think, yeah. Okay, for every edge, we take a column. And then I want the elements of the subspace, curly F, to correspond to the rows. For every element of the subspace, not just a basis, you can't just take a basis, it doesn't matter. Take the whole subspace. We take a row, and we write down this element of the subspace, just the images of the individual edges as they're assigned. So you get a 1, 0, 0, 1, 0, something, 1, 1, 1, 0, 1, 1, 1, 0, 1, and so on, just something for every element of the subspace. And we're going to use that in linear algebra. If you have a linear function, for example, coming from a matrix with matrix multiplication, the dimension of the image of this function plus the dimension of the kernel equals the whole dimension of the vector space from which you start. And that proof, as you have seen, is going to be independent of any field that you use. So it doesn't matter whether we have a finite field like F2 or the complex numbers or the reals or whatever. So we're going to use this dimension formula for the rank of a function of the kernel. Now, what's the dimension of this matrix, the rank of this matrix? Well, we know the row rank, right? And that is precisely the dimension of F. Okay, because we wrote the elements of F as the rows. Now, you proved in linear algebra that the row rank equals the column rank. That was a non-trivial thing. So we also know that the dimension of the columns is the same, namely the dimension of F. But the column rank is the dimension of the image of this map. Right? So the dimension of the image of this map equals the dimension of F. And that plus the dimension of the kernel is going to be M. Now, what is the kernel? Well, the kernel consists of all those elements of the edge space which give 0 in their dot product with every element of curly F. That's the definition of the kernel, but that was also the definition of the orthogonal subspace. Right, so the dimension of the kernel plus the dimension of the image, which is the column rank, equals the row rank equals the dimension of F. And that's why we have the dimension formula as you know it, despite the fact that we're over a finite field. Okay, so next comes the cycle space. The cycle space is the subspace of the edge space that is generated by the edge sets of cycles. So when I say cycles in the context of algebraic aspects of graph theory, I often mean edge sets of cycles, not subgraphs. Okay? So the edge sets of cycles generate something, and the subspace they generate is called the cycle space. Okay, the elements of the cycle space in English will be called algebraic cycles, just to distinguish them from graph cycles. In German, we have two different words, which is nice. Kreise für Graphen und Zyklen für elements of the cycle space. Okay, so here is a very simple characterization of the elements of the cycle space. So just for topologists amongst you, who's been in an algebraic topology course? None of you. Well, in that case, I won't say very much about it at all. So the cycle space would consist of the one chains with zero boundary if you view the edge space as chains rather than cochains. Okay, never mind. So let's prove this equivalence that I wrote up here. The first statement is that a given set of edges is an element of the cycle space. So it's generated by cycles. It's a symmetric difference of cycles, a repeated symmetric difference of some cycles. And let's prove from that the third statement that all the vertices in this result of taking the symmetric difference, i.e. in our given element of the cycle space, induce an even degree at every vertex. And that is easy because cycles do that. So when we generate an element of the cycle space, we start with cycles. From them, we generate these elements. A cycle has the property that its edges induce even degrees at every vertex. There may be other vertices here, right? Their degrees are also even. Right, and when you have generated one and you have generated another such thing, so maybe there are some more edges here, so this is a slightly more complicated element of the cycle space for which we've already shown that the degrees induced at the vertices are all even. And then along comes another one, like this one, and we take the symmetric difference between these two. Well, what happens? We delete this common edge, right? When we do that, we preserve the parity of the degrees because when we have a vertex at which we deleted an edge, well, it was there twice. That's why we deleted it. That's why we deleted it because it's in the symmetric difference, and therefore we're losing 2 by deleting it. So we preserve the parity, and since both these parities were even, the sum of these two parities is even, and then after deleting, it will still be even. Okay, so we've proved that every element of the cycle space induces even degrees at all the vertices. The statement 2 in the middle between the two says that an element of the cycle space, every element of the cycle space, is not only generated by cycles, but generated as a disjoint union, right? We're talking about edge sets. Disjoint union of cycles means edge disjoint union now, or disjoint union of edge sets of cycles. Right, so why is that true? Well, let's use that every vertex has even degree induced on it. And so take some subgraph whose degrees are all even, and let's try to prove that this is a disjoint union of cycles, not just a symmetric difference of cycles. Well, what do? We just pick an edge, and then pick an orientation of that edge, and then keep going. And we keep going no matter where until we hit a vertex that we had before. And when we do that, then we have found some cycle, namely from the vertex that we hit along the way we traverse the edges until the point where we hit it again. And that cycle, which is all the edges we traverse except for this initial bit, that is some cycle that we have found that lives in this subspace, and we now delete that, by which I mean we delete the edges. Okay, that preserves our assumption that all vertex degrees are even. Right, we're deleting 2 at some vertices. Okay, so we have another element of the cycle space, and we can proceed in the same way, and delete another cycle, delete another cycle. And the cycles we're deleting are obviously disjoint. Okay, so we are still missing one implication, that if the edge set is a disjoint union of cycles, it's generated by cycles, and if you have a lot of time, you can do that as homework. Okay, any questions? None? Okay, then that's all I want to say about cycle spaces. So let's make a cut and do something different. And talk about the cut space. Okay. What's a cut? A cut is any set of edges that arises as the edges across a vertex partition in a given graph. So take any vertex partition, and a reminder, a partition in my graph theory courses is always a partition into 2 non-empty sets. Not necessarily 2, but the partition sets are always non-empty by convention, by my convention. So if you have such a partition, and then you look at all the edges across, that set of edges is going to be called a cut. Any such set of edges is a cut. And the cuts form another subspace of the edge space, right, viewed as sets of edges now. I won't repeat the equivalence anymore. So this is different from what we had with cycles. We said the cycle space is generated by the cycles. Now the cut space is not only generated by the cuts, but the cut space, I'll show you in a moment that it is a space, a subspace, actually consists of the cuts, well, plus the empty set which we need to make it into a subspace. Okay, so all the cuts and just the cuts together with the empty set, form subspace. And here's why. So we have to show that this be our graph G. We have to show that when you take the symmetric difference of two cuts, then you get another cut. So let's say here is, I indicate a partition of the vertex set by a vertical line now. That's like this vertical partition. So we have all these edges across now, and so on. That's our cut, say D. And then we have another cut, which I indicate by a horizontal line with some edges across it. And can anyone see a vertex partition whose corresponding cut is the symmetric difference of D and D prime? Yeah.
We can take the top right and bottom left.
Yeah, that's right. This is one partition class, and the rest is the other. And you can look at it, and you will see that the edges across this new partition are precisely the symmetric difference of the two sets of edges across the former two partitions, the cuts D and D prime. So for example, this diagonal edge here, that used to be in D because it goes from left to right, okay, but now it goes blue to blue. So it's no longer in the symmetric difference. But then it shouldn't be, because it's not only does it go from left to right, it also goes from up to bottom, from top to bottom, which was D prime, with which we took the symmetric difference. So that edge rightly does not lie in the resulting cut. That is the sum of D and D prime. Now, that wasn't a proof, right? So you have to look exactly where are all the edges, what can happen, and so on, and then actually sit down and prove. It's an easy exercise, and I won't do it for you. It used to be in the book, and it was so simple that I banished it from the book. It's now an easy exercise. Well, the exercise consists in finding this idea and then checking it, not in being told the idea. And that is really boring. So anyway, why could I afford to banish it from the book? Well, because it follows from another fact, and that is what you see here, that the cut space is generated by what we call the atomic cuts. The atomic cuts are those sets of edges that are incident with a single vertex. So if that vertex is little v, then I call that E of v. Okay? These are the atomic cuts. And they generate all the cuts. Why is that? Well, easy peasy. Take a given cut. Which atomic cuts would you use to generate that? Which little v's do you take? Yes, correct. So you take all the v's in one partition class. Right, and then you sum over all the E of v's for all the little v's on the left. And what edges do you get? Well, there may be edges in here, but you get those twice. You get those in E of this v, and you get it in E of this V, in 2 atomic cuts. So these edges will occur in this sum of E of V's. So sum over all V in class 1 of the atomic cuts twice. The edges across will occur exactly once because they're incident with only one little v in V1. So that is going to be the cut F. Right, now let's look at some particular special cuts, which are called bonds. Bonds are the minimal non-empty cuts. A bond, by definition, is a cut that is non-empty, but it has no subset that is still a non-empty cut. The minimal non-empty cut. They're called bonds. Now that's just a definition. Let me breathe some life into that definition. So suppose you have your graph here and it has many components. Then a partition of some of the components versus the other components is an empty cut, or witnesses the empty cut. The edge set, the set of edges across this partition is the empty set. And those are not the cuts that we're talking about at the moment. We're talking about cuts that are non-empty, and amongst those, we want the minimal ones. So the minimal cuts of any component are non-empty, and in fact, they are also going to be cuts of G. You just have to complete this partition of the component, and you can do that. You just put all the other components on one side and you're done. So the minimal cuts of a component are going to be non-empty, and they're going to be bonds of G. And every bond of G arises in this way. Now, if the graph G itself is connected, then there's a useful characterization of those cuts that are bonds, and that is, it's all those cuts where both partition classes induce a connected subgraph of G. Okay. Right, if you have such a cut, there is not going to be a proper subset that is still a cut, because if you're missing one edge, then you can get from any vertex to any other vertex. So the cuts into into connected sides are going to be bonds, and the bonds, conversely, every bond is a cut of a connected graph into connected sides. Okay, so why are bonds important? Well, they're the same for the cut space as the cycles are for the cycle space. Namely, they are the minimal non-empty elements. But now by definition. Right? So the cycles, the edge sets of cycles, were the minimal non-empty elements of the cycle space, because every element is a disjoint union of cycles, and you can't get any smaller than having only one disjoint cycle. So the cycles are the minimal elements of the cycle space, and the bonds are the minimal elements of the cut space. Now, let's prove for cuts, what we proved for cycles, namely that every cut is not only generated by the bonds, but is in fact a disjoint union of bonds, right? So remember the proof that we had for the cycle space. What did we do? Well, we found in a given element of the cycle space, somehow, cleverly, one cycle, we deleted that, and then we said induction. Okay? Can you do that here? You have a given cut. That's a given cut. Can you find in it a bond, deleted and continued? So here's our cut, any cut. Can we find a subset that's a bond? Come on. Think of the definitions. What's a bond? What's the definition of a bond? A minimal non-empty cut. So we're starting with a cut, right? If it's empty, then, okay, it's generated by anything because it's the empty set. So that's fine. We only have to generate the, then it's the disjoint union, namely over an empty set of bonds, and that's fine. We have to show that a non-empty cut is also a disjoint set of bonds. So we're given a non-empty cut. Can you see a subset of it that's a bond? Yeah? Yes, of course, of course. All right, so if this is not itself a bond, it's a non-empty cut, but not a minimal one, then we delete edges until it is minimal, right? So it definitely has nothing to do with graph theory. It has a subset that is a minimal such animal, namely a bond. Right, now comes the interesting bit. Now, when we did the cycle proof, we said, okay, we delete this set of edges, and we notice, we're preserving the condition that we had, namely that every vertex has an even degree induced on it, because we're deleting at every vertex 2 edges or none. And so we would like to have the same here, that if we delete this bond, then the rest is still a cut. Huh. Yeah.
So one of the vertex sets has to be split at the boundary where we cut the edges.
Yeah, but that's not going to be, I mean, it's not going to look as it does in this picture that we say, okay, this is a bond, and now the other edges form a cut. Well, between what? In order for an edge set to be a cut, you need a partition of the entire vertex set, not only of half the vertex set, so that this set of edges is the set of edges across. And it's non-trivial to find these two vertex sets. Right, so we have a cut. We have a subset of the cut, which happens to be a bond. We delete those edges. Now we have some edges left. We want to show that this is a cut. What do we have to do? Well, we have to produce a vertex partition such that this remaining set of edges is the set of edges of all the edges across that other partition. Now, how do you cook up such a new partition? No idea. And still, there is a half-line proof that this is indeed a cut. Not the elementary pedestrian proof where we produce the partition and say, oh, look, it's the set of edges across it, but by some other means. So the trick is that the entire set minus the yellow set, which is what we want to show as a cut, equals the entire set plus the yellow set, because we're over F2. So the remaining edges are simply, or if you like, a difference, but they're also a sum of two cuts, of the cut we started with and of the bond that we found in it, whose vertex partition we also don't know. So we have a sum of two cuts, and that's a cut because the cuts form a subspace. So abracadabra, this set of edges down there is a cut, and we have no idea what it cuts. Isn't that brilliant? Okay, so we do have the same statement for cuts as we do for circles, namely that an arbitrary cut is not only generated by bonds, but is in fact a disjoint union of bonds. Now here comes the pedestrian proof. Can we see this disjoint union? Okay, let's make a bold attempt. We have a cut, and we want to see how the set of edges across, lots of edges across, I'm going to draw some in a moment, how these edges across appear as a union, disjoint union of bonds. Okay, the two partition sets might be connected or they might not be connected in G. So to make it a little more general, let's assume they're not. And here is an obvious naive candidate for a bond. So we pick a component here and pick a component there, and we take all those edges. Are those a bond? I mean, they're certainly minimal, right? Because if you delete one of these edges, then you can get from any vertex here to any vertex there. I cheated in many ways just now, or I was just being stupid. No, they're not even a cut, right? They don't have to disconnect the graph G, because you might have an edge here, and then another edge there, another edge there, another edge here. Sorry, that's not what I wanted. Back up there, right? So after deleting the yellow edges, it may still well be possible to get from this set of vertices to that set of vertices with the edges we haven't deleted. So those are not the bonds, the entire set of edges between a component on one side and a component on the other side. So how can we see the bonds? Well, let's take this connected subset X of V1 and draw a new picture. So this is X, which is connected. And when we delete that from the graph, we get some components, obviously, as we always do. And components are also connected. Okay, then we can consider the edges from X to each of the other components. So this y here was connected in the complement of x. So that is certainly inside some component. But there may be other blobs from this picture that are also in the other component. For example, x sends an edge to this. So we have some yellow edges, and we have some other edges. Now, those edges certainly form a bond. Right? So where's the vertex partition? That shows that it's a minimal non-empty cut. Well, it's non-empty because it contains the yellow edges. Ah, well, I didn't tell you that there are yellow edges. Okay, let's do this. Let's do it in a connected graph. Right, so these edges form a bond. Where's the vertex partition? The component is on one side, x is on the other side. And then these things here, these components here, well, they'd better be on the side of x. But then this is really the set of all edges across this partition. So that is a cut, and it's minimal because both these sides are now connected. Right? The graph is connected. Okay, so we found a bond that contains at least the yellow edges. These and a few more, like those ones, sorry, wrong picture, those ones. Now can you see the disjoint union of bonds that our original cut is?
We decide for one side and take into all the connected components.
That's right, yeah, yeah. We just do that for all the x's here. Right, for every x, we get some set of edges from this picture, and we don't really know where they go. They go to some combination of components on the right. If they go to a component, we must contain all the edges to that component, right? But we don't know which components offhand. But if we do that for one x, and then we do it for another x, we get another bond. And these two bonds are edge disjoint because the edges from the first are all incident with the vertex in x, and those from the second are not incident with the vertex of x. So those are going to be edge disjoint. We just do that for all the component on the left, and then we have also covered all the edges across the cut. So we have found some disjoint union of bonds, and that union must be the original cut because we've covered all the vertices that emanate from the left. Yeah, okay, good. So the first statement says that the cycles in a graph are precisely the cycles in its blocks. I mean, that's obvious. Every cycle lies in some block. That true? Yes.
So the block is the same as the connected component?
Excellent. Excellent. In order to prove something, first lecture, first year, it helped to look at definitions. So what is a block? Oh, a block in my course is a maximal subgraph that has no cut vertex. Right? So I don't define blocks as some authors do as maximal two connected subgraphs because we have bridges as well. So you remember the block cut vertex tree? You have a block here and a block there, and they overlap in single vertices, but you might also have just a single edge there, and that we also want to call a block. That is not too connected. So our definition of, our sort of slightly artificial definition of block is a maximal subgraph that has no articulation point, no cut vertex. And that inspires a one-line proof of the fact that every cycle lies in a block. Can you see it? Well, a cycle is a subgraph without a cut vertex. So we take a cycle, and then we add more graph until it's maximal with this property of not containing a cut vertex. And then that, by definition, is a block. So trivially, by definition, every cycle is contained in a block. Okay, is every bond contained in a block? Let's look at the picture and try not to use the picture, just to guide us, but let's try and make a formal proof. So we have a block, and we want to prove that this block lies in one, we have a bond, and we want to prove that this bond lies in one block, in some block. Okay, maybe not. Okay. Now, let's pick an edge, any edge from our bond. That lies in some block. Now, the edges of that block, of our bonds that happen to lie in this block, these yellow edges, but not those. These yellow edges, I claim, separate x and y not only in the block B in which they lie. So B is the block by definition that contains this edge. Every edge is clearly contained in some block, and B is the block containing this edge xy. Some other edges from our bond also lie in B. Maybe some don't. I want to show that those that do separate x and y, not only in B, which is pretty obvious, but also in G. And the reason is that if you had a path from x to y that avoided those bond edges that lie in B, so you go into some other bond, other block, and then somehow you return to y and you don't really know how, okay, you could invoke the fact that the block vertex tree is in fact a tree, and then prove that if you got round here, you would have a cycle of blocks, and it's all a bit messy and complicated. But there's an easy argument, and that says that if you had a path that avoided these yellow edges, this path couldn't leave B, because then you'd have a B path somewhere in G, a path that starts in B and ends in B and is otherwise outside B. But then B wouldn't be a block, right? Because B is cut point free. B plus this path is still cut point free. So B was maximal with this property. Okay, so there can't be an edge, a path from X to Y that leaves B. But if it stays inside B, then in particular, the edge or edges of our bond, which it must cross because the bond separates X from Y in G somehow, must lie in B, because the entire path doesn't leave B. Okay, so we have shown that the edges of our given bond that happen to lie in B are, in fact, a cut of all of G, separating X and Y. That means, since yellow was a minimal cut, non-empty cut, that there aren't any other edges in other blocks. Okay, so our given block is a subset of, our given bond is a subset of one block, and it clearly is a cut of that block, namely it separates the, X from Y. So the vertex partition that it induces on G has X on one side and Y on the other side. So on B, this also induces a cut. And we want to show that it's in fact a bond in B, right? Remember, we want to show that every bond of G is in fact a bond of some block. Yeah, so we have to show that we can't dispense with any of these edges here if all we aspire to is to be a cut of B. But the argument for that is the same. So if you had a smaller subset here that would still separate B, then in fact it also separates G, because you can't have a path that leaves B and comes back. So same argument as before. So we have shown that the bonds of G are in fact bonds of a block. And if you do have a bond of a block, then that also separates the vertices that we can extend the partition of that block to a partition of G into two sets, which even in G it separates minimally by the same argument. Okay. Right, questions about that? Yeah.
I'm a bit confused about the bridge above B to left, but I guess both bridge vertices are part of both blocks.
No. That's a separate block by itself. Okay, so if we started out by our bond in G and said, okay, pick an edge of that bond that lies in some block, it might lie in this block. Then it would be that block. That would be the entire bond of G, and then, is that a bond of, yes, it is a bond of K2. Yeah. It's a minimal set, it's a non-empty, a minimal non-empty cut, indeed, of just this K2, right? Yes, it is. Any other questions? Okay, so last little observation. We have some equivalences. For any pair of edges of G. Call them little e and little f. And then for a given little f and little e, the following three assertions are equivalent. The first is that they belong to the same block, to some common block. The second is that they lie on some common cycle. And the third is that they lie on some common bond. Okay. Now, before we look at the proof, which is easy, of course, why is that interesting? Can you see an aspect of the first assertion that is not obvious for the second and the third? Belonging to the same block. Is an equivalence relation. right? Because the blocks partition the edge set of G. Belonging to some common cycle is not at all obviously an equivalence relation. Belonging to some common bond is not at all obviously an equivalence relation. But the lemma says that they are, because they mean the same as belonging to the same bond. Right? So that's useful to know. Belonging to some common bond or belonging to some common cycle is an equivalence relation. If this belongs to some common bond with that edge, and this edge does with that edge, then these two also belong to some common bond, no matter how, no idea how to generate that. Right? Well, yes, we do from the statement. Right? Okay. Right. So let's prove that. If we have two edges in the same block, do they lie, or maybe I can use this picture for the start. Here's an edge, and there's an edge. Do they lie on a common cycle? Well, yes. Because if they're two distinct edges in the same block, the block is not going to be a bridge. Right? If the block is not a bridge, then it's two connected. And then we can use Menger to do that. Maybe they cross. Not cross in the sense of intersect, but maybe in the picture they go like this. But we can't choose which vertex goes to which in Menger, but we certainly get a cycle to which these two given edges belong. You don't have to dig out Menger's theorem to prove that. There are elementary proofs as well. One, for example, is from the way two connected graphs are generated. Remember, by tacking on H-paths, that's graph theory 1 early on. Okay, so if two edges belong to the same block, they belong to some common cycle. Now, it's a little more fun to prove that if two edges belong to the same cycle, they belong to the same bond. Right, that's the third statement. Why is that? I'll draw it in a way that almost tells you the proof. So here are two edges belonging to some common cycle. Find a bond in which they both lie. Yeah?
Because there is no single vertex in the cycle to hold the cycle together, so there's a single vertex to move to connect bonds.
I didn't get that.
Maybe I have not yet grasped.
Yeah, okay. What do we want? We want to find a bond, in particular a cut, to which these two edges belong. Well, in order to get a cut, one way to try is to find a sensible partition and then say, yeah, the cut that I want is the set of all edges across. Well, you can see a little bit of a partition in this picture already. Right, so this part of the cycle should be on one side, that part of the cycle should be on the other side. If we ever have the two yellow edges in some bond, this bond will separate those two. Well, yeah. Okay, but there are many more vertices in G. But never mind, just see what happens. Our graph is connected by assumption. No, it isn't. Yeah, it is. Look at any other vertex, and then you travel through this cycle until you hit. And you just remember that path. and then take another vertex, travel to this cycle until you hit. If you like, if you hit one of the earlier paths, you can also stop there. So in this way, we connect every vertex to this cycle, and some vertices happen to get connected to the left portion of the cycle, as split by the bond edges, the prospective bond edges, the two edges that are on that cycle, versus those that hit the cycle on the right. Okay, but we've done that for every vertex in G. Remember, our G was connected. If it isn't connected, if there are other components, just put them on one side later. Okay, but then we have our partition, right? Okay, so all the edges from left to right now certainly form a cut because they are all the edges across some partition into non-empty vertex sets. And is that a bond? Yeah. Now we invoke this useful little observation that we had earlier. When the graph is connected, the bonds are precisely those cuts where the two vertex partition sides, the two sides, are connected, or that come from a pair of sides, which, by the way, is going to be unique, that are connected in G. Okay? So this is connected because, by definition, it consists of all the vertices of G that have a path to the left half of C, of this cycle C, that avoids the yellow edges. Yeah, it doesn't matter. They're just edges, so have a path to the left side. And this is going to be connected because that bit of the cycle is connected, and what hangs on it is connected to it. And similarly here, this is connected, and what hangs on it, off it, is connected to it. So we have a vertex partition into two connected sides, and that is a cut, which is also a bond. So we have found that our two sets of edges, that are two edges that lie in some common cycle, also lie in some common bond. Okay. And now to complete the equivalence, we need that edges that lie in the same bond lie in some common block, but we proved that a moment ago.